don't like it. And this happens in a few very classical examples. Okay, so I'm going to give you two examples to illustrate the point. You see where classical logic doesn't really do the job. And obviously, nowadays we have many different classical logics. They are each for different topics, different applications. But let's look at historically how it came out and why classical logic doesn't work for a lot of other applications, right? So the example involves some minimal mathematics, but I don't expect, you actually don't need to understand the mathematics to understand it, but it needs some very simple things. So the only thing it needs is called a rational number. It's called a rational number. Example, and we need some concept called a rational number. Okay, so for those of you who are online, have you heard of rational number? What is rational number? Do you have any idea what is a rational number? You can actually Google if you don't remember. So it should be a concept that is taught about in high school. So a rational number is a number that can be written in a fractional form. Okay, so if n can be written into, let's say, a over b, where a and b are natural numbers, then it's a rational number. Right, so examples, any natural number, any integer is a rational number, right? So 2 is a rational number because it can be written as 2 over 1. Right, so any natural number is a rational number. 0.5 is a rational number because it can be written as 1 over 2. Right, 1.5 is a rational number because it can be written as 3 over 2. Anything can be written as a natural number over another natural number is a rational number. Okay. We also have cases such as 0.333 dot dot dot. You can have infinitely many threes there, and that's also a rational number because it's 1 over 3. Okay. But there are some counterexamples. Some numbers are not rational numbers. So begin with pi. So pi is what is pi? Pi is 1.34 something something something. Right? It's infinitely many long, and it's not a rational number. Right? You can never write pi into the format of something over something. Right? It is not a rational number. Another example. So usually we use a letter E to mean the natural constant, or sometimes called the Euler constant. If this constant is a 1.27 dot dot dot, it's also infinite. And that one is also not a rational number, right? You cannot write E into a natural number over another natural number. So the third counterexample, square root of 2. What is square root of 2? It's about 1.44 something, if I recall correctly. Is it recording? Okay, good. And you cannot write square root of 2 into something over something, right? So counterexamples, got 3 of them, and that's sufficient for us to illustrate the point. Okay. So the first proof that we've got is the task is to prove that at least one of e plus pi and e minus pi is irrational. Okay, at least one of them is not a rational number. Okay, at least one of them is not a rational number. And this is a kind of mathematic proof that, if I don't show you the proof, you may take days and weeks and years. Right? It just needs a little thing that clicks, and then it connects everything. So I'm going to show you the proof, and the proof is actually extremely straightforward. Okay, so how do we prove it? We prove by contradiction. So proof by contradiction. So how do we prove by contradiction? We assume that both of them are not irrational numbers. We assume the opposite of what we want to prove, right? So assume that both are rational. So that's the opposite of what we want to prove. Okay, so what do we get? But then we say we can add them up. We can add them up. What do we get? We get 2 times E. Okay, and we know that 2 times E is irrational. So this guy is irrational. So if the sum of these two numbers are irrational, then at least one of them's got to be irrational, right? So something's wrong with the assumption. Okay. So the assumption is wrong. Therefore, we have proved that at least one of them's got to be irrational. Because if both are rational, then their sum should be rational, but it's not. All right, so that is proof. It's extremely straightforward. Okay, proof by contradiction, and we've proved it. And you can see something here. Something's up here. And what some of those mathematicians are not happy with it is that we never gave any evidence in this proof. So we're asked to prove that at least one of them is irrational, and we've completed our proof. But now we still don't know which one is rational, which one's irrational. So that's okay. So we've completed our mathematical proof, which is legitimate or is totally valid, but we didn't give any evidence which one is valid, which one is rational, which one is irrational. Okay. So that's part of the reason why some mathematicians are not happy with it. Because some mathematicians think if you give me a proof, you better give me an evidence for every step of your proof. You need to give me some concrete evidence. Right? In classical logic, this is valid reasoning in classical logic, and it allows people to give a proof without evidence.
Right.
Okay, so here's another example. So prove that there are 2 irrational numbers x and y such that x to the power of y is rational. Okay. So here's our second task. The second task, we're going to give some examples. Okay, we're going to give some examples, but those examples are not really the evidence that we give. All right, so here's our proof. Assume that x is square root of 2. Okay, right. Actually, so what we actually want to consider is square root of 2 to the power of square root of 2. Okay. And y is square root of 2. Okay. So let's consider what is x to the power of y. It would actually be that, right? Which is square root of 2 squared, which is just 2. Okay, so we know that this guy is irrational. So the only question is x irrational or not? If it is irrational, then we found the examples. We found the evidence. If it is not, right? If it is not, then we'll just say x is square root of 2 and y is square root of 2. And that because under that assumption, this guy is not this guy is not irrational, so it is rational. Again, we have another example that satisfies what we want to prove. Right, so it's like we have two cases. This is case number one, that's case number two. But we actually don't know which case is true. But what we're proving is it doesn't matter which one is true. We cannot, either as long as we know one of them is true, and that's sufficient for us to give up to complete the proof, right? So it's almost like we give some examples, but they're not really direct evidence to support the proof. And again, we completed the proof. There's no evidence, right? We show no evidence. So if you imagine this is a court, right? So you lodge a case in the court. This is not going to convince the judge. So you show no evidence at all.
Yep.
And yet this
I
is
told you so.
this is classical logic. This is classical logic. So mathematicians thought about, okay, so what's weird here? So which part of classical logic is not good that allows us to give this kind of proofs without evidence? So they found, okay, proof by contradiction is apparently a bit of a problem here. All right, and what is proof by contradiction? It really says, assume that A is not true. Okay, and if that's not the case, then what you derive is A is true. So the principle here, right? So the point I want to illustrate here is just double negation elimination. So this is what mathematicians find out. So in classical logic, you can do double negation elimination. And that's one of the core sources of these kind of proofs that allows you to do the proof without giving any evidence. Okay, so the example below here is it's called the law of excluded middle. As it says, A is either true or A is not true. It's called the law of excluded middle. So classical logic supports these two kinds of valid formulae. Right? And then mathematicians said, okay, what if we don't want them? So probably 100 years ago, around that time, the mathematicians thought, okay, we're going to invent a new logic. That new logic is going to say it's the same as classical logic, except these two guys are not valid formula. They're not valid formulae in this new logic. So we want to forbid these kind of proofs. Okay, so that new logic is called intuitionistic logic. And it comes from this word called, it's quite complicated, it's called intuitionism, right? Intuitionism. And it actually has a synonym, and it's called constructivism. So in other words, people say a proof is a constructive proof if you give an evidence for every step of your proof. Otherwise, it's not constructive. So intuitionistic logic is also called constructive logic. It's also called constructive logic. So this, if you do reasoning in this logic, so you're confined in a way that for every step you've got to give an evidence. It's called constructivism. Some people really like it. Right? It works really well in some applications. It doesn't work well in other applications. It's like there's no silver bullet that can fit in every application. Right? So it's almost, so nowadays it's almost like there's a spectrum of things. And I think Dora in the online audience would know the other end of the spectrum. So the left end of the spectrum, let's say, is called constructivism. It says you need to give me evidence for everything. to convince me. And the other end of the spectrum is called, it's called zero knowledge. Right? It says, you need to convince me without giving me anything. Or you need to convince me without giving me any evidence.
Okay.
And, you know, sounds a bit counterintuitive, but I actually found many applications in cybersecurity. Because in cybersecurity, there's a very important concept. It's called information leakage.
Okay.
Okay, so if you give a proof, give a constructive proof, you know, other than convincing people, you're leaking a lot of information there. There's a ton of information there. All the evidence are there.
Okay.
Right? Zero knowledge proof is the other way around. You need to convince me, but you need to show no evidence at all. And that's also very tricky. That's also very tricky. It's also very tricky. So there are a ton of different logics, right? So a ton of different logics in this spectrum, and classical logic goes somewhere in the middle. Right? Classical logic goes somewhere in the middle. So this is some of those motivations why people would need different types of logics. Another motivation is to really look at different aspects of the mathematics. So here's an interesting thing about mathematics. All right, so maybe you can tell me, so in your high school subjects, what subjects did you have in high school?
Like I did math B, English,
Math, English,
drama.
drama.
Oh, this is reaching back a bit now.
Okay, so that's
yeah,
probably,
music. I think was the other one.
so
yeah.
that's probably, so let's take two examples.
Yeah.
Math and English.
Yeah.
Right, so let's take math and English. And let's think about philosophically, what problems are they solving?
Well, I guess you kind of think like math is like your logic, numbers based, data driven kind of stuff. And English is more communication and human stuff. That kind of the direction we're going.
Sort of. But you can see it's actually not easy to distinguish them in a single word.
No.
Right?
Yeah, and in English, why would you hide any information? I mean, you just want to say something. You usually say everything. You don't really hide anything. Prove something in English or in any language for that matter, like human languages. I mean,
Human language. So I think we're getting somewhere. So the way
I would probably put math in the middle because that has like it's not just like it has several directions within math. So like it has one side which is like, oh yeah, only the constructible proof which I can see, and it also has this other type of logic as well. So I would put that in the middle because it has several directions. And
it's like the way they express things kind of different. So this actually, so some mathematicians looked into this, and not even sure if they're probably not just purely mathematicians, they're also philosophers, right? So they thought about this, and then they figured something out. So what they figured out is they kind of had this distinction called it's called intension. It's called intension and extension. It's called intension and extension. And they're actually quite similar words, but different meanings. So there's also the other word called extension, like spelled out like that with a T instead of S. And that's a different word, right? So that's not the word we're talking about today. The word we're talking about today is intension versus extension. And then mathematicians and philosophers back then thought it's almost like the majority of mathematics is talking about extension, whereas English and literature and that sort of the other side of the studies, they're looking at intension. So what is really intension and extension though? The way they define this might be slightly different than the definitions in dictionaries. So they say extension, it is the way that you designate objects. Okay, so in other words, it's the external meanings of things.
Okay.
And intention includes some internal meanings of things. And then they decided most of the mathematics are talking about the external meanings. They're talking about what things designate without looking at the internal meanings. And that's what they sort of decided. Okay, so it may sound kind of weird. So we need some examples. All right, so let's talk about them as extension is the designation of objects. Okay, so designation of objects, and intension includes all the other meanings. So what is this designation of object? All right. So in your mathematics class, what is the most common thing that you see?
Like your symbols and numbers,
Symbols, numbers, and
X and Y and that sort of thing,
yeah, and they together they form
like a formula,
equations.
yep.
Equations, yeah. So what is an equation? Equation. So something equals something.
Yeah.
Right.
Yeah.
What an equation really means is it's telling you that X and Y, the left-hand side and the right-hand side, designate the same object. That's what equation means. So that's the reason why mathematicians decided this is what mathematics is, extension. So all we care is extension. Right, so we say 1 + 1 = 2. Why? Because 1 + 1 designate the same object as 2. And that's everything that mathematics, well, most of mathematics care about. Right?
Yeah.
Whereas English cares about some more, intrinsic meanings. So let me give you one example. That's a very classic example. Very classic example. It's called morning star versus evening star.
Okay.
Example is called morning star versus evening star. Okay. Now, what is morning star? What is morning star?
It's the star you see in the morning, it shines the brightest.
Shines the brightest.
Yeah.
Right? So it's one of the planets in our solar system. And which one is it?
Venus? Mars, Venus. It's Venus, isn't it?
It is
Yeah,
Venus.
there we go.
It is Venus. Okay. So we can write an equation there. You can say morning star equals Venus. Okay. What about evening star? What is evening star?
It's the first one you see in the evening, shines the brightest.
Yeah,
Yeah.
that is true. Which one is it?
Is it also Venus? I'm not sure.
Anyone in the online audience? Not sure.
I've never thought about them being different, so it's not.
Okay, so you are not sure. So tell you that is also Venus.
It is also Venus. Yeah,
It
there
is
we
also
go.
Venus.
So even though they equal the same thing, we're thinking of a different
Okay.
time.
So now with mathematics, we can safely equate them. Right? So we can add the equal sign, say they are equal. They designate the same thing.
Mhm.
Okay. So that's mathematics. Now the problem arises when we think about this. Morning star equals evening star.
Hmm.
Right. So a few minutes ago, you were not sure. So if I if I told you morning star equals evening star, you've learned something. You've learned something, right? But if I told you Venus equals Venus, you would think I'm wasting your time.
Duh.
Yeah.
Yeah.
Right? So that's the
Right.
problem here. See, from mathematics point of view, from extensions point of view, these two sentences, they're equally valid.
Mm.
There's no way you can distinguish them. Anything that you can connect with an equal sign, you can substitute the left with the right, nothing changes.
Mm-hmm.
But clearly they're different. All right, so there's some sort of meaning that is more than just extensions. Right? And that is the intention. That is, that is not usually, it's usually not what mathematics study. That's what English studies.
Right. Yeah. Gotcha.
Right? So it's a very classic example to illustrate, it's difference between mathematics and English. Right? And there's an even better example, but it gets too complex and it gets too philosophical, right? So the other example is it's called Clark Kent versus Superman.
Yeah.
Okay,
They're both the same.
so if you knew the comics, if you knew the DC world, you know that Clark Kent is Superman.
Yeah.
So makes sense to write Clark Kent equals Superman. And that's okay,
Mm-hmm.
right? Mathematically, doesn't seem to be anything special, But then, somebody looks at this and said, look, Clark is a pretty common English name. Kent is a common English name. Pretty sure there are, thousands of people in the world, probably more millions of people called Clark Kent. So the concept of Clark Kent exists. It's a real concept,
Mm.
right? But the concept of Superman doesn't exist. It's made up in comic books. So how can you even, equate something that exists with something that doesn't exist? I mean, there are a lot of identity crises that comes out from this.
Yeah.
So, in mathematics, obviously, we don't study that. That's part of English,
Yeah.
right? So that's intention. Here we only care about extension. And that's so I kept saying that's the majority of mathematics, but there are still some parts of mathematics that actually talks about intention, talks about something that is more than just extension, right? More than what they designate. And that comes to some other non-classical logics. So the concept there is called modality. The concept there is called a modality. And the modality tells you some sort of belief. Some sort of belief. You think that something should be in a certain way. And that's a bit beyond what extension is. Okay, so there are a few very common modalities that we usually talk about. So it's usually possibly something is possibly true, right? And that's obviously that's not part of classical logic. Because in classical logic, we don't talk about something is possibly true. We talk about something is true, but something is not true.
Yeah.
Right. Sometimes you want to talk about something is true in most cases, not be true in some other cases.
Right.
It's true in some of those scenarios, so sometimes true, right? And there are some other modalities. It's always true. And so from there, people have developed a ton of different modalities to talk about things. And then there were other non-classical logics. So just, I think, previously we've talked about intuitionistic logic. there were also other, it's called modal logics. Modal logics. Plural, so it's actually got many different variants of modal logic. So obviously it's got some modalities, and we usually use the symbol, a box, to mean. So in modal logic, what's happening is we're no longer staying in a simple world where everything's true or false and there's nothing in between. Where we're looking at different possibilities, and the way those different possibilities are represented in modal logic. So it's almost like almost like you are in the MCU world and you've got different universes. Right. So modal logic is basically looking at them as if you can reach a different world from your current world. And there are different ways you can connect to the next world. And the two main differences, one is called, from one world you can reach, from one world, box A is true, means that every world that is reachable from there is also true. Okay, so imagine you are here, and this world can reach the 3 other worlds. Okay, so if box A is true here, that means every world that A can reach makes A true. A must be true everywhere that A reaches. Okay, and diamond A says you are here, and diamond A is true here, and you can reach 3 other worlds. Then at least one of them makes A true. Could be this one. Could be the one on the top, one at the bottom. Okay. So it sort of gives you different ways to express possibilities. And then there are other sorts of non-classical logics that talks about time. So the example is linear temporal logic. Okay, linear temporal logic. And it's also got this kind of modalities, but they mean different things. So it's being linear. So the belief there is, we believe that the world is a linear time step. Okay, it goes in a straight line.
Yep.
So, but it's discrete. So you go from this point to the next point, to the next point, to the next point, to the next point. But they're just different time points in the straight line. And you still have things like box A. So what box A means is that if box A is true here, then A is true everywhere that follows. Okay, it's called always true. A is always true. Okay, so if box A is true here, then A is true at every following 10 points. Right? And then it also has diamond A. So if diamond A is true somewhere, that's another example. Take another example. If diamond A is true here, this is called eventually true. So sometime in the future, A is true. So it could be true here. Or it could be true somewhere here. It doesn't matter where A is true, as long as sometime in the future it is true. That's what diamond A means. So those are all things that you can't really express in classical logic. You cannot really express in classical logic. Another example, so is something called linear logic. It's not linear temporal logic. It's not about time. Linear logic. So what linear logic is about is talks about resources. Talks about resources. So in classical logic, when you say A, what does it mean? The interpretation is that A is true. It's true.
Yeah.
So if A is true, then multiple copies of A is also true. Right? The notion of copy is almost like it doesn't exist there. A and A, A and A and A and A, the same as A.
Mhm.
So if A is true, then A and A is also true. A and A and A is also true. All right. But if you want to reason about resources, then it's different. So, so it really depends on how we interpret this formula that we write. So what if we interpret A as I have a copy of A? If I have a copy of A. That's the way you interpret A, then suddenly just because A is true doesn't mean A and A is true. Just because you have one copy of A doesn't mean you have two copies of A.
Mm.
So suddenly you need something more than classical logic to reason about these kind of things. Okay, so linear logic, it introduces some special way to connect formula. It uses a star. So A star A means two copies of A. Right? So that allows you to reason about how much resources you've got. And that's clearly something that classical logic doesn't allow us. Right, so I think that's basically most of the looking at different forms of logics. So classical logics are all well and good, right? But it doesn't really allow us to do all sorts of different things. So for that reason, people have invented a whole bunch of different non-classical logics.
Oh, well, that.
It's crazy. So
Yeah.
everybody invents a different logic these days.
Yeah, right.
So somebody even combined some of them.
That's a
So,
good job.
I think that was before my PhD time. It's probably somewhere in the early 2000s.
Mm.
So somebody said, okay, I want to reason about computer programs. And previously there was some, existing work about it. So there was the mathematician Tony Hall, the guy who invented quicksort. Right?
I know that one is.
So that's
Maybe I'm.
quicksort.
Oh, quick sort. Sorry. Yeah. Okay.
Okay, so
Yeah.
quicksort is one of the most efficient sorting algorithms, and it's invented by computer scientist Tony Hall, and he later won the Turing Award, which is a big deal. Right?
Yeah.
And he also invented something called OR logic,
Okay.
and that logic is for reasoning about computer programs. And everything went well for a long time until somebody decided, okay, OR logic doesn't allow me to reason about computer programs that manipulate memory resources.
Hmm.
It's based on classical logic.
Yeah.
Right? It cannot reason about resources. So somebody said, okay, I want to look at computer programs, but I also want to reason about, your resources, especially if you free up some memory. I want to check if it actually happens. Most of the segmentation errors, all those sort of bugs, they actually come from incorrect memory or pointer manipulation. So we want to reason about it, and you cannot do that with OR logic. So somebody extended that with some new logic. This new logic is called separation logic, and separation logic sort of goes back to this concept of linear logic, that it allows you to say, you've got a memory resource like this. I can separate that into two parts.
Mm.
Maybe one part is A and one part is B, and then I can look at what's happening with part A, happening with part B.
Yeah.
And there are lots of things that you cannot do in classical logic, but you can do it with separation logic. So sometimes it's sometimes it's not really a good trend because that means everybody can invent new logic. And then it's, nowadays, I don't know how many logics we've got, not all of them are useful.
Yeah.
So sometimes people invent a new logic for the sake of it, and they never get used.
That's fun. How do you decide which logic you use? Is it just the resources that are there, or?
I think you need to look at the application, you need to look at what you want to do.
Yeah.
If you want to reason about time, you've got to use some of those logics that can talk about time.
Yeah, right. Yeah.
Right? And if the time you're looking at, it's a linear timeline, then you probably use linear temporal logic.
Yeah.
Sometimes it's not. Right? And there's something called computational tree logic. It's called tree. It's not a single line. Right? So this is basically extending linear temporal logic. It's also got those temporal things, but it expands with multiverse.
Yeah.
So
Right.
you've got multiple universes, and we can talk about something is true forever, but in all the timelines, and something's true in the future, but in only some of the timelines. It's a computational tree logic, and it's a lot more expressive than linear temporal logic, but that also means it's a lot harder
Yeah. Okay. Yeah.
than linear temporal logic.
So there might be
So-
some things like that you can use for a lot of things, but like it'd be way overkill.
Well, yeah, so
Yeah.
I guess, just now you asked, how do you choose? It's got so many logics, how do we choose which one we use? So the other thing, I guess, besides you look at the application, you look at what you want to express. You also think about their complexities. So how difficult is it to solve a problem in this logic? And they're all different. They are all different. So I think we will continue this discussion about complexities next time, but in the brief overview, so the first logic that we looked at, the propositional logic or classical propositional logic, it's actually pretty hard already. Okay, so theorem proving in propositional logic. So this is basically the simplest logic, right? This is the simplest logic. But theorem proving, so proving valid formula, and the other problem is called set solving. So try to decide if a formula is satisfiable or not. It's already so-called NP complete. Okay, so theorem proving and set solving, they are NP complete. Right, so NP complete means it requires a non-polynomial. Well, it requires a Turing machine to solve it in non-polynomial, non-deterministic polynomial time. It's called non-deterministic polynomial. And in algorithms and complexity theory, there's a boundary between what's called tractable and intractable. Right. So basically, we look at that from a complexity theory point of view. Some problems are really simple. Right. So it takes constant time. So it's right O1. It takes constant time to solve it. So take an example. You got an array. You want to know the value of the third element in that array. It takes constant time.
Yeah.
Right.
So you just check like one, then you check two, and then you check
You
three.
just pick that one.
You check that one. Yeah.
You don't need to check anything else.
Oh, right. Yeah.
I only want to know the.
Yeah.
I don't even need to check out the other ones.
Yeah.
Constant time to solve it.
Gotcha.
Right. But you can go up a little bit. So you got an array of numbers. Well, let's say those numbers range from 1 to 10. and you want to find which element of the array is largest. And you want to find the largest number in
That's
that
value,
array.
yeah.
Okay, so if you go through the array and check, it takes linear time.
Yeah.
The arrays of size n, you need to check n things.
Yeah.
Right, but then there's something called binary search, which makes it quicker. Right, so if you do it linearly, it's called linear time. All right, and it's it's a bit harder than constant time, but it's not too bad. But if you've got an array and you want to sort the array, you want to sort the array from the smallest to the largest. Okay, so quicksort, if you know quicksort, takes n times log n on average. So I shouldn't use big O something, but on average it's n times log n. It's not too bad. All right, but if you use a sort of brute force method, you probably need 2 loops,
Yeah.
and that would take n squared.
Yeah, 23.
That would take n squared. Right, and that's still not too bad. So back when Tony Hall invented quicksort, it was going from n squared back to n log n. It was a big deal.
Mm.
I'm not sure if I've talked about that example of the Americans population recording. So they usually they need to go through their whole population and sort of do some filing and sorting, and then figure out how many people are there in the country and what are their names, what are their addresses,
Mm.
right? So before 1960s, they collect all the information and they sort everything, and it takes about 10 years to sort it.
Yeah. By
By
that
the time-
kind of relevant.
Yeah, it's irrelevant. And then quicksort, significantly changed that into a couple of months.
Oh wow,
That's crazy.
that's incredible.
So it's a big deal going from n squared to n log n. But nowadays, even n squared is sort of easy for today's computer.
Yeah.
Right? So in effect, nowadays, if you've got an algorithm that goes into the constant a, as long as that a is constant, we sort of say that's those are tractable. Tractable meaning today's computer can they can solve them easily.
Yeah.
Because we've got very powerful computers. But if you got a problem with complexity of constant a to the power of n, and n is growing with the size of the problem, suddenly it's a big deal. So this is called exponential.
Mm.
And then today's computer is not that good to solve it. Right? It will take a long, long time.
That makes sense.
And sometimes you also got things like n factorial. It's really hard, right? Really, really hard. Sometimes you got something even worse. You can have double exponential to the power of n and then to the power of n. That goes really bad. It goes really bad. So those guys are called intractable.
Right.
Means today's computer can't really solve them efficiently. And NP complete says the best solution we have today is intractable,
Mhm.
but maybe there will be some better solutions that are tractable. We don't know.
Mm.
Right, so that means, as far as we're concerned, for today's technology, it's not that efficient to be able to solve these kind of problems.
Yeah.
So it's NP complete. In the future sessions, Sammy also want to talk about something that goes even beyond those guys, called intractable. So there's a whole theory of computability. This is some problems are not computable at all,
Right.
and that's not good. So
Yeah. No.
so those guys, I mean, some are efficient, some are not efficient for today's computers, but they're computable.
Yeah. So at least you can do it, even if it might
Yes,
take you forever.
compute them. But then there are guys that are called incomputable. Some people say uncomputable, but I think the mathematical term is incomputable. So you cannot compute them. and that's really, really bad.
Yeah. Makes sense.
And maybe in some of the future sessions, we can talk about it. So one of the examples is to that it also comes from Turing machine. That's why this guy Turing is, one of the biggest guys in computer science.
Yeah.
All right. So when he looked at his Turing machine as a computational model, he said Turing machine can compute everything that is computable.
Mm.
Then there's something that Turing machine cannot compute, and he demonstrated that, and that sort of broke mathematics. Because before that, there was a mathematician, German mathematician called David Hilbert, and he was one of the top guys in the 1900s.
Yeah.
And he said, he was very confident, right? He said, everything can be solved. If we cannot solve it, that's because we don't have that technology yet. That's because we don't have the mathematics to solve it yet.
Yeah.
And then somebody else, Turing, and then this Gödel, they came along and said, look, we've got a problem and we have proved that you cannot solve it.
Right.
That's it. So it's a famous problem called the halting problem of Turing machines.
Right.
It's a halting problem. It sort of simulates if you run a program, you're given a computer program, does that program, terminate? So do you know if there's an infinite loop in your program?
You hope not.
You hope not, but
But it can be.
there's no way that you can decide. So the point is, there's no way you can decide that problem, deciding if your program will loop forever or not, is incomputable. So there's no way at all to decide this.
Because it can't run it to check it, because if it loops, it'll never finish.
Right, so
Yeah.
maybe we can talk about
You're
it
right.
time. Right, next time.
Wow.
So today's session,
Oh, thank you very much.
problem.
Thanks everybody online. I'll stop that recording.